In this video, we shall present a utilitarian interpretation of differential privacy. Recall that differential privacy aims at avoiding harms to users whose data belongs to the differentially private database. Utility theory gives us a setting to model this harm and thus to bound the potentially negative effects to users. Let us assume that each user has a non-negative utility function whose value may be affected by the response of the differentially private mechanism. Indeed, when a response R in R is returned by the mechanism, attackers are susceptible to use R to make a decision f of R that impact the users, hence leading to a user's utility of U of f of R. Now, differential privacy cannot bound the value of U of f of R, but epsilon differential privacy does bound its expected value, or rather, a user's utility will be mostly unchanged, whether he remains in the database X or is removed from it. Indeed, we have the expectation of U of f of R when R is drawn from M of X is equal to the sum over all possible responses R of the probability that M of X is equal to R times the utility of f of R, and by epsilon differential privacy, this will be at least the sum over all R of e to the minus epsilon times the probability of M of X minus the user equal to R times U of f of R. Now we've used differential privacy on the term probability of M of X equal to R. And this will be equal to e to the minus epsilon times the expectation when R is drawn from M of X minus user of the utility of f of R. Now, the interpretation for epsilon delta differential privacy can be derived from the interpretation of delta we gave in the previous video. Namely, for epsilon delta differential privacy, there is a small probability delta of uncontrolled privacy breach, in which case consequences of attackers' actions are potentially unbounded. But apart from this small probability event, our previous reasoning holds. A user's utility will be mostly unchanged. This mechanism has interesting consequences for game theory in general, and mechanism design in particular. Namely, differentially private mechanisms are mechanisms for which any agent's action will likely have no significant effect on its utility. And interestingly, this implies that for differentially private mechanism, truthfulness will be an approximate Nash equilibrium. More precisely, if M is an epsilon differentially private mechanism with epsilon at most 1, and if utility functions are bounded between 0 and 1, given that by misreporting the data, any agent transforms the truthful database X into a database X prime at distance at most 2 from X, a similar computation as the one we did earlier shows that the expected utility of M of X prime is going to be at most e to the 2 epsilon, so the 2 here corresponds to the distance between x and x prime, of the expectation of U of M of X, which is at most, so we can use the fact that we have the inequality e to the x at most 1 plus 7x for x in 0, 2, and this allows us to bound the previous quantity by 1 plus 7 epsilon times the expected utility for M of X. Now we can develop this expression. This gives us the utility of M of X plus 7 epsilon times the utility of M of X. Now the utility of M of X is at most 1 because the utility is upper bounded by 1. And this gives us the utility of M of X plus 7 epsilon. And thus, for epsilon differentially private mechanism with epsilon at most 1 and utility functions between 0 and 1, truthfulness will be a 7 epsilon Nash equilibrium. So differentially private mechanisms are almost truthful.